We're currently recording. I'm sharing my screen. So since you're all keeping pace with the programming, it's less of a problem. I just want to make sure that we're on the same page with things and that you keep pace with the class. So I owe you a couple of things to be graded, and I will take care for that promise this weekend. I am a little behind because the day job has been super busy as well. Things are just where was in before. I'm bringing this a little back, a little bit more wiggle room. Okay, so we are doing today, we're talking about power calculation and analysis of variance, and this is also what we will be discussing in the lab today. So how was graded lab? Any feedback on the graded lab? How did things go with table 3? It is quite an involved setting, I am well aware.
It was very tedious. It was very tedious.
Quite long, honestly. It's really long.
Yes, but
yeah.
keep in mind, this code you will have forever.
What?
You have this code at your disposition from now on.
Yeah.
You can work for this for all table 1s that you essentially will have to compute over time. Hi, how are you? Thanks for coming. So, and this is a very useful code essentially, and you will really benefit from having this at your disposition. Okay, so I'm sharing my screen. You can see my screen, I hope, well. I'm going now in presentation mode. First, this one. Script. Okay. Okay, excellent. Okay, so we're starting now with the part of the entire class, which is the introduction to population-based research and study design, which essentially is a really important piece when you do analysis with data like you, for example, have at your hand with the NHANES. Part of this is also power calculation, as you can imagine, because the power will determine how much the sample size is that you will need for any prospective studies. And it will also determine your ability to actually detect the difference in your data between sample populations and population, as well as between two sample populations. So we will do power and sample size calculations corresponding with Open Intro 4.6. We will do analysis of variance, talking about the concept and the motivation of a simple one-way ANOVA. We will not talk about two-way or more-way ANOVAs, but there are ways that you actually can take more than just one parameter into account and conduct multi-level analysis of variances. We will also discuss the interpretation of an ANOVA table. I will talk about post-hoc testing. Also, there's a quiz. Oh, yeah. Thanks for reminding me. Oh, then I stopped sharing me. Thanks for the reminder. Okay. Is Sharp going to join Monday? You know?
Rishabh's in the meeting, Professor.
Yeah, he is, Sharp. Hi.
Hi, Professor.
All right. Yes, you're right. Today's quiz. I keep on forgetting the quiz. That's the second time now. Okay.
The Canvas settings have it locked until 8.
Yeah, I sent you the access code in a second. Oh. Okay, access code coming in the Zoom chat. There we go. Good luck. It shouldn't be terribly difficult. You're not going to have a hard time. Drop me chat messages in case you have questions. You should have ample time. It should be fun.
I don't know. I don't have anywhere to put in the access code. It's not asking for it.
Yeah, the professor, the quiz is closed.
Try again. Now it should work. Please leave the cameras on while you're taking the quiz.
Professor, the quiz is still closed. It shows logged until November 11 at 8 p.m.
Yes, professor.
Oh, I didn't save it. Why didn't you save it? But I'm sorry. Okay, now it's saved. You also have a formula cheat sheet in case needed. That may be helpful. Then you're basically able to increase the sizing difference, and you make sure that this difference is really as large as it can be with that intervention, or you increase the intensity of the intervention. Secondly, you can decrease the standard deviation, which is usually done with increasing the sample size that you're sampling. This also goes hand in hand with the third point, where you increase the sample size, where smaller sample size limit the power. And yeah, for two sample tests, the best power you actually would assume if there's equal variability and the sample sizes are equal. And you have reduced significance level, which essentially will also allow for you to make assumptions in a more robust, in a more powerful way. So this is power calculation in a very fast way explained. I think what's only important are the codes that we will be discussing and the principle. And I think the principle is somewhat easy to grasp, that it's really one minus the beta, where beta is essentially your risk of committing a type 2 error. Are there any questions to that so far? Or shall we move on? We have 40 minutes left, so it's less time this time. Any questions from you in Zoom?
Not yet, Professor.
Okay. All right, then let's move on to ANOVA. We will talk about it again in the lab when we do the coding. Okay, the learning objective of ANOVA. So the ANOVA essentially for a one-way ANOVA is you need to do 5 different points. So you need to understand the motivation. You need to know why you're essentially doing an ANOVA rather than a t-test. You need to be able to look at the underlying assumptions that an ANOVA has. You can carry out hypothesis tests for several population means that you consider equal, and you interpret a one-way ANOVA table, which we'll do later. And then you can carry out post hoc tests to essentially look at each individual difference. What an ANOVA is in principle is what we will be discussing now using the same example as the cell phone study. You remember the 2 sample means was the cell phone study. Now we're getting a third group. We're getting now voice and data. So you remember we had use of a cell phone and your reaction time to braking, right? Versus no cell phone use and braking. And now we're using voice data, so you're messaging. You're not only speaking on the phone, you're also messaging something. And what is your resulting reaction time as compared to those that did not use a cell phone at all? So now you get a third group to that. So with two groups, it's easy because you only have mu1 minus mu2, which is equal under the null hypothesis. If you're adding a third group, you get basically three different groupings and three different reaction times. So if you want to see a significant difference here, you could hypothetically go that pathway that you compare each group individually. That is a method 1 versus method 2, method 1 versus method 3, method 2 versus method 3. So this is in this context, it's a different example. It's a learning example. But it basically goes the same pathway. We have three different groupings. If we would compare each group individually, and these are the outcomes. So they are substantially different, right? So you can see already that this one is likely going to be significantly different, which is also reflected here by the mean times, right? This is 12 and 10 versus 22. But you cannot judge it. You cannot approach it in that fashion just by looking at the mean, which would be essentially violating the rules of predefined hypothesis in trial design. You essentially would need to define your hypothesis beforehand, before you even do an analysis. This is important in the context of research. So you could do it by approaching it with 3 t-tests, right? But the problem is that each test individually will have a 5% chance of a type 1 error, which is not a problem if you do it for one group comparison. If you do it for 2 group comparison, it's 1 minus 5% squared. If you do it for 3 groups, you basically have 1 minus 5% to the power of 3. So you end up with essentially a probability of making a type 1 error for each of these comparisons of 14%. So this is obviously non-acceptable, and this will exponentially increase with the number of groups. So this increases even further. So what you need to do for that is you need to change your hypothesis, your null hypothesis, in a way that you can make inferences without going down this pathway to accept such a high risk of committing a type 1 error. And this you do with an analysis of variance. You are taking into account the variability within one group, and you compare it to the variability between the groups. So this essentially is a graphical depiction of this data. So you have 3 normal distribution now, where one is substantially different. This is where you use voice and data while trying to learn something. And so we know this sample statistics, and you know the null hypothesis. So now when for an ANOVA, for a one-way ANOVA, you essentially assume under the null hypothesis that all 3 groups are the same. So as soon as you get a significant result in an ANOVA, you have the insight that under the alternative hypothesis, at least one of these groups are different from the overall mean of all 3 groups. So this is your research hypothesis. The advantage of this is that the ANOVA is robust against type 1 errors. And here are some assumptions that are to be made from ANOVA. So you need the sum of all these groups need to be less than 15. So it's not allowed to have more than 15 groups. When you have a considerably large sample size, it can get problematic, but you even can get away with moderately skewed data. Thirdly, you need homoscedasticity. That means that the variability for all 3 groups needs to be comparable. So it shouldn't go greater than a factor of 2 in difference of the standard deviation within the groups. It's more conservative when this is violated, but it is problematic. And you also have non-parametric approaches to that. where you don't make assumptions about the homoscedasticity, but we're not discussing this in the context of this class. And thirdly, you need to make sure that all of these group assignments, that the groupings are basically part of independent samples, so that these are not in any way related. So what we will be doing later for the lab is we are assigning them in tertiles. We are assigning blood pressure entries in tertiles. So this is on paper essentially to some extent violating these assumptions because they are somewhat related, but you can still employ this. Okay, so it's got to be independent random samples that are drawn from G populations, and subjects are randomly assigned separately into the 3 groups. And you're quantifying 2 different standard deviations. You're quantifying the standard deviation within the groups. So this is the variance within the groups, calculated in the same fashion as we did it before. And you are employing a between standard deviation. And the outcome between this is essentially that the variability between the groups, the variance between the groups, divided by the variance within the groups, gets you to the F statistic. And this F score is just like the T score and the Z score to be compared to an F table, which I want to show you quickly. And you essentially, you get to an F score table. And this F score table, just like with the T score table, so you're comparing it in an F statistic, which is a unimodal skewed, right skewed distribution. And the resulting F score is being read from this distribution. And with the predefined critical value here on the F, you basically can say whether you reject or not reject your null hypothesis of all 3 groups being equal. So what you need for that is essentially you have degrees of freedom in the denominator, which are your within group samples. And then you have the degrees of freedom in the numerator, which are your groups. But your groups -1 because it's the degrees of freedom, right? So you will read here the critical value, and with your F statistic that you get from your ANOVA, you essentially can now say whether your ANOVA is rejecting the null hypothesis or not, based on the F statistic that you're calculating. So, this being said, we have here an F statistic, the variance between divided by the variance within. Does that make sense so far? Any questions? From anybody on Zoom? Question? So it's really comparing the variances between and within the group, and based on that you get an F. And this F will allow you to essentially read it against your distribution, against the F distribution. And based on that, you can then decide upon whether you accept or you reject the null hypothesis. So this is basically how you would calculate it, and how the distributions look like at different degrees of freedom, and how you can basically make a decision based on the judgment or not. So here, essentially, you see the same graphically displayed. Again, you have a critical alpha level, and if your F statistics is exceeding that, you get a resulting p-value, and this p-value essentially is the probability that you're seeing this due to this difference due to random chance, or this is indeed a difference, a really significant difference. You reject the null hypothesis if the p-value is below the significance level of 5%. So if we're going to the training program again, to this learning with either no cell phone use, with cell phone use, or cell phone and data, you see here the grand mean, and you are looking at this difference here, and the resulting F will essentially give you an idea to what extent these groups are deviating from the grand mean. And this is the so-called ANOVA table. And this is the table that R will compute for you, and every other statistical software will compute for you. It usually contains As far as I know, for all statistical softwares, it basically contains the same information. So you have here the sum of squares, where the sum of squares we know already. So this is the deviation from between groups. This is the deviation from each group mean to the grand mean. And the within group sum of squares is the deviation from each individual entry within the group from the group mean. And this will then in total, and you see that this adds up, give you the total deviation. This taking into account now the degrees of freedom. So we've between the groups, so we have three groups, 3 minus 1 to get to the degree of freedom. That's the one that you can draw from the calculation of the sum of squares by only having 2 entries. So if you have 3 groups and you have a sum of square given, one of these group means is redundant, which you can draw. So essentially that's the definition of the degree of freedom. So if you have a sum of square given for whatever data frame, whatever data variable you have the sum of square given, and how many entries, individual scores can you draw to still be able, based on the sum of square and the remaining entries, to calculate this last entry. This will be your degree of freedom. So you can, with one group, you can drop one individual score, and you're still able to establish this relationship between the individual scores and the sum of square. The same with the groups. So you have 3 groups, you have a sum of square given, you have 3 groups, you don't need the individual entry of the third group to still be able to establish this relationship between the sum of squares and the 2 remaining groups. So this is the definition of the degree of freedom, which is important for the context of multiple comparisons, because within your data variable, essentially here you have 3 entries for the groups and a sum of squares. You can drop one, and this gets you to the degree of freedom. Within the groups, you have essentially 7 entries, and you can drop one from each group. But you have you get to the degrees of freedom. We have the number. So we have here for each group we can drop 1. So here's the data. We have 11, 16, 9, 13, 8, and 9, 18, 23, and 25. So that's 3, 6, 9, 9 minus 3 groups, because we can drop for each group, we can drop 1. You subtract 9 minus 3 gets you to the degree of freedom of 6 that is stated here in the NOVA table. So this is how you would calculate the degrees of freedom for the within group degrees of freedom. With the sum of squares, you can basically reinstate all of these 3 individual scores arithmetically. For total, essentially, it's the sum of these 2 degrees of freedom gets you to the total degrees of freedom. But what you really need for the calculation of the F is, as we remember, it's the sum, it's the variability between the groups divided by the within the groups, variance within the groups divided by the variance between the groups, which essentially gets you to an F, which essentially allows you to read it from the F distribution, whether you're going to reject it or not. The resulting significance level here is that p-value that essentially allows you to see the remaining risk of a type 1 error. Is this clear so far? The ANOVA table, this is really important because this is your output essentially that you will be reading from our output. The F statistic has this remaining p-value, that is the remaining risk of a type 1 error, and will essentially allow you to gain insights whether at least one of the methods is different. And only in this case, only if this is significant, you will conduct a post hoc test where you essentially compare the groups individually against each other. And if an ANOVA is not significant, you will not go down the pathway to conduct post hoc tests, but only if one is significant, you will essentially estimate the group comparisons. So essentially, you will do that by quantifying confidence intervals, because that gives you an idea of the within group variability. And we have seen the box plots. You can do this even more elegant with an error bar, with a 95% error bar plot. And you can then, with these post hoc tests, also look at the individual significant differences. So there are four main methods of post hoc ANOVA tests. One is the TACI honest significance testing. You can do a Bonferroni method, which we will all two see. So we will see a TACI, we will see Bonferroni. With TACI, essentially, you use the pairwise comparisons and these differences and the confidence intervals of the differences. With a Bonferroni, you will adjust the p-value that you will accept based on the number of comparisons that you have conducted. Then you have a Dunnett method and the SU method, which is essentially less commonly used comparison methods, post-hoc comparison methods. What you can basically graphically and in terms of hypothesis testing employ here is building confidence intervals. And if the confidence intervals that you're building include the zero difference, like it does, for example, here with method 3 versus method 1, you can conclude that there's a significant difference. So a difference, if there's no difference under the null hypothesis, you have the difference is, the resultant difference is 0, right? So if the 95% confidence interval of one comparison of two groups does not include the 0, you will see a significant difference. And this is to be treated and interpreted as significant difference between method 1 and method 3. Or here method 2 versus method 3. And we remember that method 3 was actually the one with the very large difference to the other groups. So this is basically different in all three comparisons. And this is a TACI HSD test, TACI honest significant difference test, which essentially allows you to look at each of these groups individually and compare the confidence intervals versus the difference. This is the graphical depiction of it, where you see these comparisons plotted against a mean difference of 0, which essentially would then allow you to see these differences plotted against the 0. Not including the 0, the significant difference. So this is 2 minus 3 and 1 minus 3. 1 minus 2 is now significantly different. So this is one way to approach it. The second one would be a Bonferroni test, which we are not doing. It's not depicted here for this analysis, but we will see it then in the lab. Okay. So the F-test tests the null hypothesis that two or more groups have identical means. It's treated like a right chi-square statistic. It's a right skewed, always positive F. And only if it exceeds the critical value from the F-score table, you will assume this to be rejected in terms of null hypothesis. And you assume normally distributed populations homoscedasticity, meaning that it is different, but it's not different beyond a certain factor, which is 2. And you have independent samples. And you use post-hoc tests only if the F is significant. Good. So that was this. This was the theoretical part of today's class with 20 more minutes for the coding. Any questions from Zoom?
What is the difference between a null one-way and two-way?
Well, the two-way includes a second parameter.
Okay.
So you take difference from a second parameter into account, and you basically look into these differences in terms of a second parameter, which increases complexity, but it also it gives you the means. So if you have, for example, you could take into account for the learning example, cell phone versus no cell phone versus cell phone and data. You could take into account age or previous education standard of that individuals randomized to each of those groups. So this would be a two-way ANOVA.
Yeah,
And you can do two-way, three-way, you can do various ANOVAs.
yeah, I got confused because I was remember one way, but what's my at night, it's like two ways.
Yes, yes, yes. So the question was, what is a two-way ANOVA? And this is essentially where you factor in additional variables into your comparisons, into your group comparisons, which does affect various dimensions of this comparison, mainly the variability of your sample. Very important question. Okay, so then let's quickly go to the lab. We have 19 more minutes. So you should have all received the practice lab module 10. It should be as an announcement posted on your canvas. I was also asked to specifically talk about the loading of the enhanced data sets and how to essentially approach this. So you need to look at these enhanced data. You need to install the package enhance and the package enhance A. And these two data sets essentially allow for you to download the tables. And I have here, this takes a little longer, so I did that beforehand while you were doing the quiz. You get for all of these tables, you get these entries, you get these variables. So if you have enhanced downloaded, you get these parameters all available, which you need now, essentially you need to investigate them. And you can do this for all of these parameters. You get here enhanced tables, demographics. You can download these. You can look at them in terms of the variables. You can look at them in terms of the dietary. You have here, in addition to that, I have posted here this introductory website, which allows you to essentially really investigate it. So if you look here at this description, this shows you exactly how to access this data and how to get this data packed into an object. So you can basically, you can take this directly from the package and you move it into an object, and you can work with this object just like with every other variables. And this is where all these variables come from. These are the variables we're working with in the lab, and you can work with these variables to pursue your research questions for the final project. So I really encourage you to study this in detail. You get here the gender variable, for example. There are examples how you get things into your R and how you can essentially work with that in R. So you can access here a plethora of different variables. You can also go on the CDC website. And you can download here data from the different waves of the enhance. This is all basically to be downloaded. This is all at your disposition. This data can all be freely downloaded without any problem. So it requires for you a little bit of digging, but all of these are basically linked with a CQN number. The CQN number or SEQN number is essentially a participant ID number that allow you to link all this data that is publicly online with the data that you have at hand from the package. So if you want additional variables, you can go through all this data, and there's like a plethora of different variables in there. And it's really not about you having data from all the waves. Just make sure you have solid data from one wave, for example, and you have data that you essentially can access and you can work with. That's perfectly fine. Just that you have an adequate sample size, try to get the sample size up to at least a couple of hundred participants. It also will be restricted in terms of data availability, whether some of the more exotic parameters, there may not be as much available. Just make sure you get a solid data set together and describe it accurately as it is. It comes from this wave. It's only wave 2013 to 14. And you likely will get a good sample size together that allows you to draw good inferences from your data. So I think that should be fine. Let me know if questions. Let's initiate a context and the conversation on this topic. Don't forget that it's due next week on the 18th, right? I think on the 18th it's due, right? So this is next week, Thursday. Don't wait too long and get in touch with me. Did you already start working on things? Did you investigate a little bit?
Start.
Yeah. Okay, sounds good. So also to everybody on Zoom, please make sure to get in touch with me early enough that we can have a conversation about things. Once you give me your research question, an approximate idea on how to address and analyze the data, we can then refine the analysis and the analytic plan and the analytic approach that you've chosen. And I will also go into the literature and find you some publications that I think are relevant, which may help you or not. You may choose your own publications, but I think it's a good process to build up your research questions along these lines.
Is it important that the the analysis that we do, or we make a plan out of it, should be like complicated, or any easy analysis would work?
Well, it's not going to be complete, but it should be a loose idea how you want to approach things. So usually what I would recommend is like to do a group comparison. So to have a comparative part of this analysis where you really compare groups against each other. And then secondly, also approach it in a correlational fashion, which we will discuss later on. So this is going to be lab 12 and 13, not lab, module 13 and 14. We're going to speak about regression and correlation. And I think it should also be part of this, but this we can determine later on once you have a vague idea how you're going to approach things.
So right now, all we need to submit is an outline analysis plan and a little details, what we are planning to do, not the code or anything, right? Or do you want us to write some code as well?
No, not yet, not yet.
Just the analysis plan, what we want to do, and any references that you plan to do ahead.
Exactly. So an analysis plan, how you want to approach things. Then we have 3 weeks for the coding, and I think this is ample time that we can get the coding going.
All right. Also, Professor, can you change the practice lab submission date? It's due, showing it's due Sunday.
Yes, I will change the due date. No worries.
Thank you, Professor.
Not a problem. All right, so I hope this was a little helpful now. Let me know if any further questions. And now we can basically focus on the lab because I also want to move forward with this. So I have posted, for the sake of time, I've posted the final code. And you will see the practice lab. Really take the time to go through the practice lab and study the questions. So essentially we're doing power analysis today. And we're doing practice lab module 10, and we're doing an ANOVA. So we will today, so it's 3 fragments, it's 3 parts of it. So part number 1 is a power packet, is a power calculation where we're comparing data from a plant RCT, and we want to quantify the sample sizes needed to detect the difference with a power of 90%, 0.9. We're assuming for part number 1, we're assuming a small effect size, a medium effect size, and a large effect size. So the effect sizes, we know how to calculate those, right? It's essentially the difference divided by the standard deviation. And then we have here a proportional comparison with, oh no, this is actually also, no, I took out the proportion. If you need a code for proportional analysis, I can give you that. So this is now essentially an ANOVA, where we have a small effect size, medium effect size, and large effect size, with different group sizes and group numbers. So you have here the library power. This is basically so the library power essentially is the power calculation for R. Once you load this, and you probably need to install it. So if you install a package, you go in packages, you go and install, and here you can PWR will allow you to download the power package. Okay. So this should run without problems. I don't think there should be version mismatches. So library power. So now we have here in power t-test. So if you conduct a t-test, it will prompt you. And if you go on question mark pwr.t-test, you can see the different parameters. So you can approach this from every different angle. You can essentially have your number of observations. You have an N, you have a D, you have a significance level, power, type, alternative. So essentially here it's basically predefined in a way that you only have power. So we want a power of 90%. So you enter power of 0.9. You enter Cohen's d, which is the effect size of 0.2, which is a small effect size. You have a significance level of 0.05. And the resultant here essentially gives you the number of individuals that you would need to study to detect your difference, resulting in an effect size of 0.2 with a power of 90%. And you see, this is quite a powerful tool, right? So if you have, you go in the literature and you find this blood pressure medication is effective and lowers the blood pressure by X by C millimeter Hg, you essentially can, based on this information from the literature, assuming a standard deviation that is to some extent consistent with what you find in the literature, you can use this to estimate your sample size. So if you have a small effect size, a small d, you will need a larger sample size than when you use or when you assume a larger effect here with 0.5, then you only need 85. If you assume effect size of 0.8, which is quite a substantial effect size, you only need 33. When you assume now a study where you conduct 36 subjects and you want to understand what your power is, you just rearrange the function. And here essentially you would see a power of 91, assuming a D, a Cohen's d, an effect size of 0.8. So this is how you can rearrange this formula. And this is how you can rearrange and get different parameters out of your power calculations. Is that clear so far? Any questions on that? Equally, when you have an ANOVA comparison and you want to know with 5 groups and an N of 78, you want to achieve an F of 0.2 at a significance level of 0.05 with a power of 90%, you see here what your N needs to be to essentially achieve that power that you desire to have. So you can, again, you can change all the dimensions here based on what your assumed effect size will be and what your desired power will be. So here's, for example, here's the example of you have 8 individuals in each group. You have an F of 0.8, you have a significant level of 5% and 5 groups. You essentially can here find out your power based on these parameters. So this is how you can do power calculation in R. Any questions on that? We only have 5 minutes left. It's hard to explain this based on only 5 minutes. But I think it's clear in the principle when you want to approach power calculation. So this interplay is really what determines to what extent you need to prolong recruitment, increase your numbers, or intensify your intervention. So now we have here our enhanced data set. And this is essentially where we will, so this is what I meant. So usually you would not do this, but we are now stratifying our SPP tertiles. We're building 3 tertiles. We're transforming our tertiles here into 3 factors. We can with do-by, the library do-by, I also flagged this, which is a very powerful and very useful function, because with do-by you can run here summary by. You can summarize your data based on categories that you have defined, and you can use all functions that are contained here in the function part of that function. You basically do SPP as a function of these tertiles factor. You draw it from data df, which is the one that I just uploaded, and you use these functions on your data. And you can do this for SPP and H. I did it also for H here. And you can then build here t-tests between all the groups. This is how you test your hypothesis in this data. If you are doing an ANOVA, you essentially get here the ANOVA table that we've discussed before. So here the degrees of freedom for the 3 groups with the residuals, for the within group, the total residuals. With here the sum of squares, with the mean squares, we get the F value and we get a significance, right? So it looks the same as the printout in the slides, just here depicted in different R-like fashion. So since we found a significant difference in the ANOVA test, we can now run a pairwise t-test. And this is to be read in a 2x2 contingency table format. So you basically compare here tertile 1. So this is a Bonferroni adjustment method. You compare here tertile 1 versus tertile 2 versus tertile 3, tertile 1 versus tertile 1. You see here the respective p-values in the pairwise comparison. And this is essentially the code for a Taki HSD, which is the honest significant difference test. Again, gives you upper and lower level of your confidence intervals and allows for you to do a pairwise comparison. So that was fast. Any questions? I think just go through the practice lab in peace, go through it. If you have any questions, post them to the discussion board or shoot me an email. Okay?
Sure, Professor. Actually,
Yep.
I have to leave for another class.
Okay, sounds good. All right.
Thank you, Professor.
Let's continue
Thank
the
you,
conversation
Professor.
on time. All right. Have a good night.
Thank you, Professor.
Sure. Thank you.